Hi everyone. Today we're going to go over the final section of Chapter 6, which is Power, Section 6.4. And I'm going to use a quick simulation to start. There are some springs on this simulation, but I'm just using this simulation to lift some objects. So we're going to ignore the springs right now and discuss simply what power is. Power is a pretty easy concept. If we have a pretty good grasp on what work is, we'll see that power is just kind of adding something to it. But let's have a scenario where we have two people and we both give them basically the same job. I'm going to use one of these 250 gram masses for my example. And let's say person A comes over, and we got to pretend a little bit because this simulation's used for something else. I'm going to pretend this white box up here is just a shelf. Alright, so I'm going to tell two different people to raise a 250 gram objects onto this shelf. Okay, so person A walks along, comes over, does it, lifts it straight up, puts it on the shelf, walks away. And person B comes over, he does the same job, but he does it faster. It's up there real quick, lets it go, and it stays up there. So person A and person B both moved the same object, the exact same displacement, just the second person did it faster. So the question is, who did more work? And many times students will respond that the person that did it faster did more work. But remember what work is at its core. It's a force over displacement, right? Yeah, depending on angles and whatnot, we might have to make adjustments to that formula. But overall, we learned that work is done when a force is applied over a displacement, right? Nowhere in the work formula does it say anything about time. So the answer to the question I just asked about who did more work, they both did the same. Let's pretend the distance from floor to shelf up here, let's say it's 2 meters. If we lifted it completely vertically, the person A and person B both lifted a 250 gram mass, and the minimum amount of force to lift a mass is equal to its weight. So a 250 gram mass, if we take it times 10.8, has a weight of about 2,450 newtons. Actually, sorry, I didn't convert that to kilograms. Let me change that. That sounds a little high. That's about 2.45 newtons. Okay. And if we lifted it 2 meters, I'm just calling 2 meters from here to some theoretical shelf up here. The work both people did was 4.9 joules. Now, while they did do the same amount of work, there is something different they did, and that's where the time aspect comes in. The second person that lifted it up faster did the same amount of work as the first, but used more power. And power is simply defined in our notes as the rate at which work is done. So that just means power is work over time. Now, the most basic algebraic version of this formula, just be careful with if we're finding average power or instantaneous, and that all depends on basically your given information. But we usually just say power equals work over time. Now, when we break it down, remember work being force times displacement. Sometimes we have to have a cosine theta in there if there's an angle involved with the force and the displacement. But let's just keep it simple for right now. I could sub in for work, force times displacement divided by t. And if I do that substitution into the power formula, I get S over t, or displacement over time, right? And we all should know displacement over time is velocity. But what kind of velocity is that? Well, it depends. All right? If during this work, the displacement, the motion of the object was steady, then it's better than average, right? If I did a certain amount of work and the displacement over time, in other words, the velocity, if it was steady and constant the whole time, that displacement, it's actually better than an average. But if while doing the work, I change the rate of it as I go, then at best, this is an average value. All right. So if we know at best we have an average velocity while doing the work, then our power is average. But if we know that our velocity of the motion of the object while doing the work is steady and remains the same, then it could be better than average. Maybe we could call it instantaneous. All right. And since S over T is velocity, there's a secondary formula for this. We could say that power equals F times V as well. Or cosine theta in there if we need it because there's an angle involved with the work being done along the displacement. That goes back to some old stuff. All right. We could even give power in the form of some calculus terminology here, where power could be viewed as the first derivative of a work time function. But the bigger thing here is that if we know that the velocity is instantaneous at a certain moment, this could be the instantaneous power, all right? Or if we at least know that the rate of which the power is being done and the velocity caused by it is steady, then at any moment that's instantaneous. But if we're moving an object, and maybe do the shelf example, this person moves it slowly, then a little quicker, then slowly, then a little bit quicker. If the velocity doesn't stay steady, at best, when we do work over time, it's an average. All right, but don't get too crazy caught up in all that. It's just stuff that needs to be said. The main thing is that power is equal to the work over the time. So if we could calculate the work and want to know power, we divide it by time, or the secondary formula, since we could define displacement over time after plugging it in, plugging F times displacement in for work, we could replace that with a V, and power could be F times V. If this V is an average velocity, it's average power. If this V is an instantaneous velocity, it's instantaneous power. But there's not much more to say about it other than the units. So we know that work is in joules, work and energy, and we take joules, something in joules, work over time, time being in seconds. So a joule per second is a unit for power, but it was renamed. 1 joule per second is known as the watt, and that's the metric unit for power. We are familiar with watts, but only for electrical power is probably the only place, especially like a light bulb, that you guys are familiar with it. But technically a watt could be used for any kind of power, mechanical power, anything like that. But since we're used to light bulbs here, let me give you a quick example. 100-watt light bulb. Let's just take nothing fancy, not an LED bulb. Let's take a 100-watt incandescent light bulb. A typical light bulb with a filament, the older kind now, I guess, that get hot, right? A 100-watt incandescent bulb produces 100 joules per second of energy. But what kind of energy? You say light, right? Well, that's only part of it. All right, there's many different types of energy. Light is a wave, and wave is a form of energy transfer. But old incandescent light bulbs got very hot. So actually, the reason why they're not very efficient is because much of that 100 watts, 100 joules per second, is going into heat and not light, which is to no surprise why most of those bulbs are becoming obsolete with the advancements of LED bulbs. Because it's not that LEDs don't produce heat, but it's minimal. I mean, you plug in an incandescent bulb for a minute and 100-watt one and touch it, you're going to burn your hand. You could have a LED bulb of equal brightness running all day and touch it, and maybe it feels slightly warm. maybe. They're more efficient because the energy is, the majority of it is being converted to light and less heat in an LED bulb. But the point of that was just an example of what you're used to. We're going to take it in the form of mechanical power. And for mechanical power in the English standard system, we usually don't hear watts in this country. We hear horsepower. So when you want to maybe hear about the mechanical power of a car engine, you always hear horsepower. But it could be in watts because they're units that describe the same physical feature, quantity. And just FYI, 1 horsepower is the equivalent of 746 watts. Or sometimes we use kilowatts, 0.746 kilowatts. All right. Just because some students asked this question in the past, I go over this quick thing. Some kind of confusing unit. Now, I'm sure none of you out there pay your own electric bill, but if you look at an electric bill and how much you're charged for monthly use, you'll notice that you're charged for kilowatt hours used. That's an odd unit, and I really can't give you a good reason where it came from. Okay, it just is what it is. You see the word kilowatt and you think, well, that's power, right? But kilowatt hours is the unit. And remember, a watt is a joule per second. So a kilowatt is a kilojoule per second. Times hours. Hours over seconds. Well, hours could be converted to seconds, and then they could cancel out, leaving us with just kilowatts. Right? Or excuse me, leaving us with just joules. I said that wrong. Okay, because a kilowatt is a kilojoule per second. Or leaving me with just kilojoules. So what I'm saying is, in the end, a kilowatt hour is actually a weird unit for work. Okay? It's not actually a power unit because it has hours beside it. Okay? But that's just like a kind of FYI thing. You're probably not going to need to know that for anything. But just throwing it in there in the past. All right, let's jump into a couple examples and give you the final section problems. And I will also be assigning all the remaining problems since this is the last section of the chapter. Tomorrow will be an uphill interactive, and then the rest of the week we'll be working on problems, asking question Monday and test Tuesday. All right, so if you don't have your books out, if you don't have your books out, go to page 190 right now and look at example 6.9. This is a very quick one. It says each of the 4 jet engines on an Airbus A380 airliner develops a thrust, which is just simply a forward force on the airliner, of 322,000 newtons. And just for a FYI, that's the equivalent of about 72,000 pounds. When the airplane is flying at 250 meters per second, or roughly 560 miles per hour, what horsepower does each engine develop? All right, so we will have to use that conversion that I gave you, that 1 horsepower is 746 watts. But the given force is in newtons and the velocity is in meters per second, so this will come out in watts. And we'll just use the version of the formula that at least says power equals force times velocity. Use the metric versions of those given quantities. Multiply them, we're going to get a big number. We're going to get 8.05 times 10 to the 7th watts. And to convert it into horsepower, we'll just use that conversion rate, that 1 horsepower is 746 watts. And that is a 108,000 horsepower engine. So yes, it takes a crazy horsepower engine for for the jet engines on a giant airliner. The typical horsepower for maybe a typical vehicle is probably around 250 horsepower, give or take. So that's pretty big, right? But simple problem. All right, moving on to example 6.10, which is a power climb. All right. And unfortunately, if we were in school, we'd do a little mini lab with this, but we'll just have to do it in the form of a example problem. So it says a 50-kilogram marathon runner runs up the stairs to the top of Chicago's 443-meter tall Willis Tower, the second tallest building in the United States, to lift herself to the top in 15 minutes. What must her average power input be to do this? Express your answer in watts, kilowatts, and in horsepower. So we just got some simple conversions to do here in a sec. So the mass of the person is 50 kilograms. The height of the steps is 443 meters. And the time to do it is 15 minutes. Converted into second, that's 900 seconds. Now we got to think about stairs for a second. Right? And when going up a set of stairs. When we go up a set of stairs, you are moving, you're not going just vertical. But this comes out to remembering our definition of work and when you're doing and when you're not. Once you are in motion up a set of stairs, yes, you are going diagonally, and yes, you are making some turns along the way. But as you step upward, the only work you're doing once you're in motion is vertical. Because horizontally, once you get into motion, remember you want to stay in motion. And you don't need to continually necessarily push yourself anything but vertically in the eyes of Newton's laws. Might sound weird until you think about it a little bit. But the main point is, we only care about the vertical work, okay, during a stair climb like this that the person does, pushing themselves vertically. So we just use the vertical height and the person's weight, okay, as they go up the stairs. Because unless told otherwise, the minimum force needed to move something vertically is equal to its weight, unless told otherwise. All right. So we use work equals force times displacement. So the force is weight, mg, or a vertical lift, and the displacement is the height, 443. Multiply those, we get the work. Once we have work, power is work over time, divided by 900 seconds, and we get 241 watts this person used, which in turn could be converted to kilowatts, 0.241, or like it asks, using the 1 horsepower equals 200 or 746 watts. That would be the equivalent of 0.323 horsepower. Which for a high climb, 443 meters, that's a lot of stairs to go through. You're going to have a person is going to have a low horsepower. But power, a big thing about power is its sustainability. Right? Animals, people, we get tired. But if you did a power climb on steps and did a problem like this where the person only went up like one flight of steps, one small flight, like maybe in our school building, that person could, if they're going really fast, could possibly be like around a horsepower a little bit more. However, that doesn't mean like you can consistently keep that. Right? Because of getting tired, a person can't sustain a horsepower for a while. Sustainable power for a person is much lower than 1 horsepower. And speaking of that, I'll give you a brief history of horsepower. We'll end here. Where the horsepower, the idea came up, was at the time when this was studied. Watt is the guy's last name that named this unit after himself. He was asked about, since horses were the primary form of power for getting things around in those days, especially like plowing fields and whatnot, Watt did an experiment and figured out that the average type of horse at the time could sustain 746 watts for a good bit of time. And I forget how much it was, but they could do a job and sustain 746 watts for a decent amount of time. So that's where the horsepower came into play. But in the end, it's all about amount of time. You know, a smaller animal compared to a horse maybe can, for a short burst, have more power, but it's about sustaining it. Like a vehicle engine, you know, doesn't get tired easily, right? It won't get tired and wear out for many, many, many miles. You know, hundreds of thousands of miles in many cases. So when we say an engine is like 250 horsepower, it could sustain that power for a long time too. Okay, so something in power, how much power something could achieve, sometimes could be deceitful, because maybe that animal, that person, could only sustain it for a short amount of time. All right, so anyways, that's the deal with power. It's a pretty simple idea. Just know your new units. And I will be posting this video along with your new problems and the remainder of problems today.